I'm going to talk about a small library. This is mainly work in progress, small library for introducing contracts in the Elixir language. And this is something that we have started a little time ago. Okay. So the main idea is that, well, there are many things that you can do statically. But as you know, some of them require some knowledge of type systems or extra tools. And we wanted a very basic system, a very unsophisticated system to have annotations so that developers and students are able to work with a contract-based development methodology. Right? You know, this is a quite old pursuit. It begins with the terms coined by Bertrand Meyer in the 90s, and well, there are several ways of doing this. Of course, you can check the contracts statically, or you can check them dynamically. If you check them dynamically, you're losing completion in general and correctness, but in some sense, it's more approachable for developers. So it's better that they get used to introducing contract annotations in the source code. Particularly for this library, there are several specific motivations. On one hand, we are running for the third year a course on programming scalable systems at the Technical University of Madrid. And we think that this might be helpful for students to avoid some silly mistakes when they're writing Elixir programs. Also, we plan to test this methodology and library with some of our own in-house developments, like, for instance, the Machina library for testing with the state machines that we presented 1 year ago in this workshop. And that's basically the idea. Some years ago, we started a similar project for Erlang. I will comment a little bit about this at the end of the talk. And we have brought some ideas from this project, this EDBC project. So we have some interest and some previous work, so we decided to start this little side project that we hope to be useful. I mean, not very sophisticated, but hopefully sometimes simple things are more useful than very sophisticated tools. All right. Okay, so this, of course, is publicly available. You have the source code, and one of the motivations for this talk as well is to receive some feedback on the kind of contracts that we could add to our system, right? So let's start with an example. I mean, I warn you that all the examples in this talk are very basic. So let's start with a function, an Elixir function to convert a list of digits into an integer number. Well, the function itself is okay, right? There's no obvious mistake in its definition. But of course, it might be the case that we call it with a wrong parameters. Right? So there's some non-explicit requirements on the input list. Right? So we're somehow assuming that there's a list of digits, and there are many things that we can leave aside. So in this case, one possibility is to call it with some of the elements being negative, or maybe we can call it with a number larger than 9. And of course, that fits in the intended type. We managed to use a type constraint for that, but of course, the result is one, right? Okay, in this case, the problem doesn't break. So it returns a result in the expected output type. So this is a trivial case of an error that might go perfectly unnoticed. run your system and get another integer, and perhaps you can execute a little bit more, and you can realize that you made a mistake, right? So of course, in this case, we need some way of making explicit what we thought was the limitation for the input to this function. So sensibly, one would expect. I think it's sort of obvious that we don't we don't want negative numbers, because it was, in natural language, it was expressed as a list of digits, right? So that would discard any number as more than 0 and greater than 9. But maybe there are some other non-so-obvious constraints. For instance, there's an argument whether we would accept a list starting with 0 or not. So maybe one parameter considers that a list starting with 0, 042 is a valid input to the function. Maybe some other parameter considers that this is not. Both possibilities are sensible, right? But the point I want to make is that it's better if you have a way to enforce that you actually write that restriction down than just understate the requirement. Okay, so this leads naturally to the introduction of precondition contracts, of course. So in this case, as we saw, there are some part of the precondition which can be trivially expressed as a type, of course, and some other part that is, of course, it can be expressed in a sophisticated type system, but not in a very basic type system. So in this case, we have decided to consider that this is a list with all the elements ranging from 0 to 9, and also that the first element cannot be 0, you know, to make the precondition more interesting, right? So in this case, this is the actual syntax that we have. So of course we are using, as you can expect, the macro facilities from Elixir in order to the sugar. Right? Basically, all of this is a pile of sugar, and we generate normal Elixir from this. So in this case, our syntax is to define another function, which is the precondition to this function here. We recognize that this is the precondition to this function because this is the same name. And in this case, we pass an argument. It doesn't have to be called with the same formal parameter. And it means that the input to list2not has to be given this Boolean function first. Otherwise, it will raise causal exception. Okay, so we are just requiring this to be typed after and have the corresponding type than the actual function that we are annotating. Right, that is the idea. Okay, so let's move. How would this execute? I mean, in order to execute this, we just call the function with the wrong right arguments. If we call this with the right argument, we get the output. And if we call this with the wrong argument, in this case, we first call the precondition, and then what we get instead of the 83 wrong result is Corsa exception, Corsa message, telling us that, okay, what failed was the precondition stated for this function. So this is a very, very simple idea. Nothing difficult here, right? Okay, some subtleties, just for those familiar with Elixir and Erlang, we have this famous problem with improper lists, right? So in this case, we could have the problem that this fails because the precondition is expressed in this way, right? And each decimal list is expecting a proper list. Right? So sometimes we have to be careful because in a language, more or less in typed language, as Elixir, you have to be careful that you don't raise an exception yourself in the function that is implementing the precondition. So in this case, we could be more careful and add that extra requirement here. So, and that would be the final form of the precondition for this. Okay.
I'm not sure if we can ask this. Is there
pick the mic. Sorry, is there a difference whether you would move these preconditions is list and list improper to the predicate is decimal list itself? So you just said you need to be careful to not throw exception or not.
But is decimal list is the predicate that I define.
Yes. The question is, can you move the precondition into the predicate, or as an annotation onto the predicate, or does that not make sense at all?
Okay, it's a good question. Okay, so yes, because all we require is this to be a Boolean function. So we just split this in for modularity or for incrementality. But we could have added this to its decimal list because it's strange because its decimal list is a function that you could use in other contexts. So I wouldn't contaminate it with, or maybe yes. Yes, I mean, it makes sense, yeah. Okay. If its decimal list is going to be used elsewhere, and I actually require this. Okay. It depends on whether it makes sense to contaminate this with the extra requirements. Depends on the case. Okay, so this is about preconditions. So the main use of preconditions is rather than detect failures in the definition of a function, is to detect failures in the use of a function. That might be okay. So you define a function, but maybe you don't know what are the intended usage from somewhere else in your project, right? So of course we move to postconditions, which are actually the way of detecting whether the implementation of a function is correct regarding the intended meaning. So of course we have a postcondition syntax here, and it's very symmetric. So it's at post, then we use the name of the function, and then we call another function. In this case, we don't call it overlist. In this case, we are checking something about the result. So result is a result where is a pronoun that we use because, of course, this code is going to be transformed into an assignment to some extra variable result from the result of list to add, and then we are passing the is integer predicate to that. So in this case, the postcondition is just an approximation. It's not a full specification, full spec for the function. It's only a type-like constraint about the result. And I think this is sensible because sometimes people just specify postconditions incrementally. So first, they want to get rid of some obvious mistakes, right? Even silly mistakes. And then they go for the less obvious ones. So first they try to get rid of some really absurd result, and then when they realize that there are still bugs in the program, they begin adding constraints. So in this case, we are not connecting the input and the output, and we will do that in the next slide, right? So of course, if we want to do for this particular case, we can do a full functional specification because there happens to be a built-in function, built-in library function in Elixir that converts an integer to a set of digits, which falls precisely in the subtype or specified by the precondition. So this is a cheap way of specifying this. That the result, if we apply digits to the result, then we get back the input. Right. Most of the time, this isn't so easy, right? Okay. So if we call the function we do a wrong postcondition in this case in order to force a mistake, we obtain a causa post violation exception. Right? It's completely symmetric to the precondition case. So most of the thing is using preconditions and postconditions in a very basic setting. But then, of course, we have more more things to show. Okay, exceptions, right? So let's make it less simple. So we have a purely functional language with inputs and outputs, but unfortunately we can raise exceptions. So exceptions are a way of giving a known result, so to say. And sometimes we might be writing the spec for a function that actually throws an exception. So we want to authorize, to say, okay, the intended behavior of the function is to throw exception in this case. So this is a little subtle. So for this case, we have contracts specifying that the functions should throw an exception in some cases. This can be tricky sometimes, in fact. It's a apparently silly thing, but it gets very tricky, as we will see in a moment. So imagine that for this example, we leave the postcondition, but we erase the precondition. So of course, exceptions happen when you somehow don't deal with all the preconditions of some functions. You have an incomplete precondition. Because if we erase it and we pass a number rather than a list to the function, in this case we obtain a postcondition violation, which is not very informative, because here the problem is that the input is wrong, right? So one thing that we can do in this case, if we want introduce the precondition, is to specify that if this condition is not met, we expect listener to throw a condition, an exception, right? I understand that this is, of course, this is not ideal. The ideal thing is to have a proper precondition, but sometimes it's not that easy to fully specify the precondition. So in that cases, we think that this contract can be useful, right? We can even be more specific and reason on the kind of exception that is thrown. Right? So here we are saying that, okay, if the input is not a decimal list, then listener should throw an exception and it should throw an exception. Right. To make things worse, there's a whole set of cases. Perhaps this is too technical, I think, right? So maybe I can leave this for the question, but basically, depending on whether you have the preconditions and the postconditions of the throws, you look to the precondition first, then the postcondition, and so on. This is a little contrived, but the message is that, okay, we have considered all the possibilities. So the basic idea for this library is that it is not ambitious. It doesn't intend to be sophisticated, but we want it to have all the possible interactions covered. So if we have three mechanisms, let's say pre, post, and throws, we want to have full, clear documentation for how these three things should interact in order the user to know what he or she has to expect from the library. So we are trying to be quite scrupulous as to document the interaction between the different annotations. That is the idea. So better keep it simple, better small and understandable than large and completely crazy and out of control. Okay, so let's go for some other. I think pre, post, and throws are the core parts of the contract thing. And I'm going to talk about some other contracts that are already implemented and some other that we are in the process of adding to the public version. So one of them is time limits. Time limits is just, say something or raise an exception if this function call is taking too long to return, basically. Of course, this is approximate. It depends on many factors, but sometimes it can be useful because there may be some case in which you're doing something wrong and it's better to notify that. So in this case, we introduce this recursive function. Well, there's a sort of obvious mistake if you want. We call it with 9, we call it with 0, and it doesn't return because as you can see, in the case of 0 wasn't considered. Right, but it is considered, but it calls an infinite recursion. So in this case, the program calling factorial would get stuck, and we capture that behavior when a second is elapsed. Right. Okay, some warnings about the use of time limit contracts. The first thing is that in this particular case, we have a recursive definition. So if we are defining this within contract, it means, if you call factorial then in this particular case, that should be the time limit in 3 seconds, right? But this is going to happen for all the recursive calls. So we are starting a timer for factorial of 0, then a timer for factorial of -1, then a timer for factorial of -2, and so on. So that can get a little bit crazy, and that increases the inaccuracy, the inherent inaccuracy of timers, right? And that's the idea. But sometimes this can be useful, but use with care. Okay, assertions. This is also considered in the publicly available version. So we allow our system to call type checks and assertions from other libraries. So the idea is, if something can trivially express as a typing constraint in using some typing tool, then use it. We encourage our students to use it, right? So you can call type constraints from inside Corsa, and we can also call some asserts at the moment using the XUnit library from Specification. The idea for the future is that you can use Corsa with a number of external analysis tools, right? So that you can access that information in a single place. Now I'm going to talk about some types of contracts that are being implemented right now. It's more arguable whether they are useful or not. But I think we have plenty of time, so we can discuss a little bit about this. So the next set of contracts that we can consider is, of course, contracts that have to do with concurrency, with communication. So if we consider that we have a functional programming language, in a functional programming language, pre and post conditions are the obvious contracts, because you have single input and single output. But if you have a concurrent functional language based on message passing, then you also have a different input of information to the functions, which is receiving messages. So that makes sense to have some kind of precondition-like construct that imposes or makes some checks on the data that is incoming to a function, right? We have considered several syntax for this, and I'm going to show one of the possibilities. So it's not necessarily the syntax that will make it into the public repo. So basically the idea is what I have written here is the assertions that would be built from this kind of contract. So the idea is the following. So we write an expects temporary name for the contract. So as to say, again, you write this before the receipt due, and you say, okay, I expect the following from the incoming data, right? So in this case, what we do is the following. So for instance, this constraint is about v, v greater than 0. So that means that this constraint affects all the patterns that contain v. Right? So we are going to extract the variables from the patterns and then generate the assertions from the specification in the expects clause. So in this case, v greater than 0 means that, okay, there's only this pattern clause that contains v, so we have to assert this here. But there are two clauses containing counter. So is counter state is a predicate that has to be applied after receiving a message here or receiving a message here. Right. So this is done in order to avoid repeating lots of checks when you have, say, 5 or 6 cases for processing the message. Right. So this is still under discussion, but this is very close to the final thing, right? Okay. Another type of contracts that we haven't yet implemented is decreasing argument contracts. We're not completely sure how useful this is going to be, but it's something that we borrowed from Daphne, which is a program with static contract checking. And this is very useful because they use purely functional specifications in order to define some of the properties. So they need termination for recursive definitions in order to build inductive proofs for lemmata, basically. So termination is very important in that case. Of course, from a practical point of view, termination is also important if you're writing recursive definitions, and you expect developers to know what they do when they write recursive definitions, otherwise you forbid recursive definitions. But okay, the idea is for some specifically hard recursion, maybe it is interesting to enforce that you are doing calls on smaller arguments each time, whatever the smaller is. So for the factorial case, we have this decreases contract that follows the same syntax as the rest of them. So if you call factorial then the absolute value of n should decrease in subsequent calls. In this case, that would avoid the problem with this function here when you call factorial of 0, because factorial of 0 calls factorial of -1, and -1 it has a greater absolute value in particular, right? So this can get trickier in general. So it's not difficult to implement, of course, but in general, you can call a function recursively in a transitive way. So just for fun, I will mention how we implement this. We keep a separate call stack for every function which is labeled with a decreases contract, and for that we maintain sizes the stack. So for example, if we have defined a quick sort function, the first time we call this, we push 8 onto the sizes stack. Next call is those elements lesser than 3. So size is 1, that would return, so we remove 1 from the sizes stack. We call quicksort with the elements greater than 3, size is 6. So here we check that 6 is smaller than 8, as 1 was smaller than 8. So at each time we just have to check that the next size that we push onto the size stack is smaller than the elements at the top of the size stack. That's the idea, right? Using the Elixir stack is harder for several reasons. One of them is for recursion optimization, that we move them from the stack. And the other thing is that you have a complete mixture of different functions. In this case, we just focus on the name of the function that we are tracing. Okay, some comments about the implementation. So, of course, as I mentioned, Corsa is implemented by program transformation. We instrument the code by reading the macros and generating more code from the absolute syntax tree of the original code. And this is basically the grammar that is supported in the smallest set, the one with pre, post, and throws, and within. Some limitations, some are temporary limitations, some really make sense. We're just allowing one annotation per function and type. So if you are annotating a function, then you're only allowed to have one pre-condition contract or one post-condition contract, not several of them. Of course, in general, contract-based languages allow for several, and there's some implicit conjunction if they're Boolean. But we didn't want to get into the trouble of reasoning about contract composition right now. So we thought it was simpler to keep it simple from the beginning. We also, as you have seen in the examples, we haven't considered pattern matching in the definition of the contracts. This we are always calling the whole input state or list or whatever. Just because, of course, pattern matching introduces the possibility of partiality, and we don't want that to happen. We don't allow for gods at the moment in the headers. So that's the idea. So again, trying to keep it as simple as possible for the moment. Okay. Okay. There are some results in the paper. Of course, this is work in progress, and the results doesn't have to be very representative. So the idea. So this is a test of the list on app example for several sizes. What is trivially instrumented? Of course, not instrumented should be obvious. There are no contracts at all. And trivially instrumented is just the type-like requirement, being a list of snapshots or whatever. And the full instrumentation has to do with this expensive thing here. Has to do with checking that it's a list of digits, that kind of thing. Right? Of course, this grows with the size of the input, so that's reasonable. So what's the moral of this? In general, of course, if you don't write just 3D type-like contracts, then this takes time, right? So fortunately, the idea of contract-based development is that you're just running the instrumented program that you're developing before you have some integration test or whatever. So you don't really care about efficiency at an early stage of the development. Of course, for the final version, for the production system, you're going to remove all the contracts and hopefully the system is running with no overhead at all. So that is basically it. Remember that things, even for this simple case, are going to have a cost. Okay, so that's it. I don't have much more to say because it is quite recent project. So we have provided a library with classical contracts like preconditions and postconditions, but we also support some less supported features like exceptions, time limits, assertions on incoming messages, right? So we also allow interfacing with other tools, and our hope is to interface with many other tools, many of your tools, for instance. There's an emphasis on simplicity and practicality. So let me talk a little bit about this EDBC story. So EDBC was Erlang design by contract work that we did some years ago. We had one paper, one workshop on functionality programming in 2018, I think. And we were very excited, overexcited about some possibilities, some things that we could do dynamically, particularly regarding concurrency, because that was our academic interest. We were very interested about different, how to use Erlang behaviors in order to enforce some concurrency patterns between clients and servers, and so on. So it was a really heavy system full of, we could even test for fairness, things like that, right? It was really, really complex at times. So we published this paper, we put the implementation in GitHub, on GitHub, I think. And some months later, we discovered that there was some discussion about EDBC in some bulletin board, Y Combinator, and apparently some programmers in California were trying to use this. And we were all happy, this is great, we have downloaded EDBC, let's have a look at the comments. And the comments were not good because the system was so crazy, was so complex at times that they didn't understand some of the features. And some of the basic features didn't work perfectly. So we learned the lesson from this. So that was an attempt. So now we are developing things with Elixir, and we want this really to be used. So let's start from the ground up. Let's introduce make the important contracts that 95% of the programmers are into use very clear. Let's build on this. Let's use, and let's just introduce more sophisticated contracts, multi-party session type checking or whatever when they're actually needed. Anyway, of course, we're going to introduce some other contracts. So we're completely open to suggesting on what would you kind of contract we would find useful in Elixir or Erlang. One of them is purity contracts. This is one of the controversial things on EDBC, but sometimes this is really needed. I mean, you need to assert that a function is pure, that doesn't have any side effects, right? And there are several ways, cheaper or more expensive ways of stating this, right? So this is a clear candidate to be added very soon. Another question is invariance. It's not clear whether we or how we need invariance in a functional language. Of course, if you look at invariance in languages like Daphne, they're used in the imperatives part of Daphne for loops. Or sometimes you reason about invariance when you have state in an abstract data type or an object. But if you don't have explicit objects or loops, it's not clear where to put an invariant. Of course, you have some global invariance, but this contract-based thing is a very local thing. I mean, you want people to write on something that makes sense at the local level. So it's not clear. So this is very debatable where to put the invariants. And of course, we're going to need some more things about concurrency and a long list of things below here. For example, John was mentioning modules. So how to merge contracts between module boundaries and so on. Many things that we have yet considered. And anyway, we will introduce only if needed, only if somebody requests. And I'm afraid I don't have much to say.
Great. Thank you very much for the talk.
You're welcome.